So downsampling has been routinely used in convolutional neural networks. They have several functionalities. One of them is reducing the computational costs of the models by basically reducing the feature map sizes. They also control the access of the subsequent layers to the information from the input image. So feature map sizes and receptive fields are basically controlled by kernel size and the downsampling operations, basically by the number of them and their positioning. They're usually done either by doing two-step, is doing max spooling, as you can see here, and then doing max spooling and then doing the convolution or doing a convolution with strides that are larger than 1. And both are equivalent. Usually in many of the CNN, we see that the filter sizes are fixed across the layers. However, when you do the pooling, although the filter sizes remain the same, the effective filter sizes basically increase. So in a task such as classification, we continuously increase the effective filter size and the receptive field as well, until we basically cover the whole image, the whole input image. It makes sense that they are an important parameter of the network. If we want to find how to downsample, basically what is the optimal downsampling, we can use either non-NAS methods or NAS method. NAS is neural architecture search, which I will explain later. So there are limited work in non-NAS methods, and what they do is usually use a continuous kernel size or a feature map by using, for example, bilinear interpolations or by using Fourier transformations. However, this is one of the disadvantages that these methods have, and they also usually replace the downsampling operations with custom downsampling modules. NAS methods, there are some works that basically search for not directly the pooling, but they search for the feature map sizes. So most of the early NAS works do that. However, they were like very highly computationally inefficient. There are also some other works in the NAS field that do the same. However, in the recent works of the NAS, where NAS has become more efficient in the recent years, however, the focus has shifted from finding the macro structure of the network to finding only the operation inside the layers. So there are not too many works that focus on this specific problem. So basically, NAS is a subset of AutoML, which is concerned with finding different architecture parameters of a network. It can be number of the layers of the network. It can be the operations inside your network. And it is a very vast field of research. Usually, NAS is separated into 3 components: the search space, the optimization method, and the evaluation method. So basically, search space is defines basically the limits of the architectures that you can find. So obviously, the less constraints you put in your search space, the more general architecture you can find, but also you will have more computational costs. So in the recent years, the trend has been moving towards using cell blocks, which basically just, as I said before, focuses on the operation inside the layers. And they usually fix the downsampling location. So this would not really be compatible with our problem. In the optimization method, which is basically how we search for the architecture, the most interesting development has been using gradient-based optimization, which has been shown to be efficient. But we will see later that this method is not really suitable for the search space that we are working with. And so after we basically do the optimization, we have to have a method to evaluate different candidate architectures that we have, so that we can rank them and select the best. So one of the most efficient methods is using the weight sharing. In this work, we use also weight sharing, but we would improve the vanilla weight sharing methods. So first, we talk about the search space design for finding pooling. In order to basically make this problem more manageable, because we're working for only classification tasks, we put several constraints on our search space. One of them is that across the layers, we can only reduce the feature map sizes. And also, we would only have one pooling at each layer. So we would not have like two subsequent poolings. So the feature map size will only be changed by one step. We also fixed the first and the last feature map size. And we just search for the pooling location. So this is an example architecture that you see here. So we talked about weight sharing and how it is more efficient than traditional methods. So basically, weight sharing uses a super network or a SuperNet that contains all the possible architectures. So it basically contains the whole search space. So what happened is that in the training of the training phase, we would train all the SuperNet together by a chosen method. So the method can be any method, basically. So basically, in this way, all the architectures that we have are trained at the same time. So so here, for example, these are like different candidates for each layer, and we train all of them together. However, when we want to evaluate, we have to sample one path in our super network, which would be the candidate architecture or configuration. And then instead of just like early works that they train each of the candidate architectures, what we do here is just we inherit the weights from the SuperNet. So there is no training required. We just evaluate any architecture that we sample by using the trained weight here. So this made NAS much more efficient than earlier versions, which used to train every candidate from the scratch, and it would take a tremendous amount of computation and time. So there are some known problems with the weight sharing. One of them is when we train all the SuperNet together, we have high memory requirements because we have to do a backward pass through everything, all the search space. So one of the methods that basically improve this is instead of training the whole SuperNet at each batch, we just sample one path and we just do the backward pass through that one path. So this is the single path one-shot method, or SPOS. Another problem is if our method of sampling favors some of the architectures over the others, then we would have a bias toward those architectures that have been sampled more. So, to ensure that everything is sampled fairly, we can use uniform sampling. And the other issue with the weight sharing is that the rank correlation between the evaluated architectures with the ground truth is low. There are this basically can be solved by reducing the amount of weight sharing. So instead of, for example, sharing the weights in the whole space, we can have subspaces where they share the weights. So the degree of weight sharing is reduced. So there are some works that basically partition the search space into sub-SuperNets. However, the problem with this works is that the partitioning is either performed manually or is performed randomly. So it's not a really intelligent way or automatic way to partition the search space. To show that the problem of the weight sharing for our problem, we chose basically we did some initial experiments. We chose a ResNet 20 architecture. So basically we took an ResNet 20 and we just searched for the pooling location. So everything else is the same. So with all the constraints that we discussed before, the search space would be limited to only 36 architecture. So we did our test on CPR10 and we used the SPOS method. So the SPOS method does the single path and it also samples that path uniformly. So the only problem that we can have is just the problem of pool rank correlation, as we discussed before. So if we take two different pooling configurations or architectures, one of them does early pooling and one of them does late pooling. If we compare the standalone performance with the performance when we have the weight sharing among those two architectures, we see that the performance of both of them degrades a lot. So it confirms that it still exists, this problem still exists in our search space. So what we propose to do to basically reduce the weight sharing is using a balanced mixture of SuperNets. So basically what we do is we always, so C here is the configurations and M is the models. So basically configurations are the pooling configurations, which we had 36. And M is the number of models which we can change. So if we have just one models, it's just the single path one shot or a SPOS method. So what we do is we always sample uniformly one of the configurations to ensure the fairness in training. Then we have this matrix of basically probability of M given C. So when we chose the configurations, then we would go and sample one of our models. So these models are totally independent of each other. So we sample one of those models with this probability, and we basically do one batch of training for this specific model that we sampled. After the training, what we do is we do one batch of evaluation on a validation batch, and we calculate the accuracy. So we use this accuracy to update the probabilities here. So basically, obviously, the more accurate model would become more probable as the training goes on. So another thing that we had to pay attention to was that we had to ensure that the probability of the models, which is basically the average here, average of this matrix, is always kept uniform. So that means that all the models are trained the same amount of time, because if we do not keep this uniform, the model that gets trained more would have higher accuracy, and then what it would result to basically most of the configurations picking that model. So and then at the end of the training, we would only, like, all the configurations, we would select one model, and that would lead to basically us not using all the available models that we have. So basically, the thing that we introduced here, which is different, is we specialize each of the models to a subset of configurations. So in this case, the weight sharing is reduced, and we later show that it results in better rank correlation and finding better architectures. So we did basically we calculated the accuracy of all the 36 configurations. So here it's the number of the layers in each basically feature map size. So here we have 2 poolings. So we would have 3 feature map sizes. So we can see here that the default and the brute force are 1.5 point different. And the model that we find is around 1 point higher than the default resonant architecture. So if we look at the correlation, so here we have the ground truth, which is the values here. And here on the y-axis, we have the evaluation accuracy. So at the end of the search, when we do the evaluation on the whole validation set, we get the accuracy here, and this is the ground truth on the test set. So when we have just one model, which is the single path one shot, we see that the correlation is low. So we have also this measure of rank correlation, which is Kendall-Tau. So the rank correlation is more important than just the correlation of the accuracies, because at the end of the day, we select the best model. So rank is more important. So we see that as we increase the M, or the number of the models, we see that the Kendall-Tau metric increases. And also we see that we have better correlation, especially with the configurations that have higher ground truth accuracy, which are the ones that are important because they are the ones that we want to find. So from 1 to 8, we see an increase. However, there is not much difference between 4 and 8 models. So it seems that there is a limit that basically after that adding more models does not really benefit the search problem. So what we did here was that basically in all the configurations or features that we had all the weights shared. That means that for example, the convolutional weights in one layer are shared among all architectures for that specific layer. So that means that basically we have full weight share. So one can argue that instead of doing this, we can assign different basically convolutional kernels or filters to different resolutions. So for example, if we have resolution or feature map size 1 at first layer, it would have a different filters than if we had a feature map size of, for example, 2. So this way, the weight sharing is reduced, and this is what people do when they deal with like different operations. So if we had instead of this problem, if we had a problem of finding, for example, the filter sizes, and we would have like 3 by 3 filters and 5 by 5 filters, and for example, 7 by 7 filters, then we could not really share the weights among these operations. So can we apply the same thing here? So we did the fully shared and not shared. So we did the SFOT method, but we also did a gradient-based method, darts, and we can see that having not shared weights does not really translate to any gain in the accuracy, and still our method would lead to better results. So it makes sense that we partition the search space the way we did, rather than the way that people who deal with operations rather than feature map sizes do. So we did a comparison with different NAS methods to see if our method is really both better and more efficient than them. So we tested 2 types of darts, and we also tested several single path methods. So the difference between these methods is that the way that they sample the architecture. So for example, if you have Monte Carlo, we sample the architectures with the Monte Carlo tree. Or here we sample with a softmax, and this is uniform sample. So here we see that our method still outperforms all of the other methods. And so if we do the darts or the gradient-based optimization, we see that because we cannot really impose the restrictions that we did previously, so the search space is more broad. So it would allow also for having basically higher feature map sizes than the previous layer, and it leads to very weird configurations for classification, because we expect it to go down, but here we would have like several places that the feature map size is increased, while basically, for example, here there is really no benefit because there is no data here. at this feature map size. We also did compare with non-NAS methods. So we did the ResNet 18 and ResNet 15 on CFR 10 and CFR 100. And because their baseline were kind of different than ours, so we calculated the gap between the baseline and the improved architecture found by this model. And we see that our results are comparable to them, while we don't really change change anything except the placement of the pooling, while they introduce additional things and different modules. So our method is much easier to adapt than theirs. We also wanted to see how it would work if we have larger images, because CFAR datasets are 32 by 32, so they're small. And also, we only had a limited search space. So what we did, we tested on ImageNet and Food 101. So on the ImageNet, we didn't really find any basically any architecture that is better than the default architecture. However, we were able to find the default architecture with our method. So the conclusion that we had was that probably the default configuration has been manually optimized for the ImageNet dataset. For Food 101, we get some gain in the font architecture. Basically here, we found an architecture that does the pooling basically very late. So it has a lot of layers that are in larger feature map sizes. So it's not a computationally efficient configuration, but we did not really pose any constraint for the computation. So we could not really expect it to find something that was not necessarily more computationally expensive. So here is the search space that we use in our work. Here for the ImageNet and Food 101, we had larger search space sizes compared to the CFAR. So basically what we did is we presented the task of finding the optimal CNN downsampling or pooling layers, which is the problem that has often been overlooked. We did extensive experiments to show that we have to design the search space more intelligently. So we cannot just naively apply the same search space design of the previous works. And we also showed that it's an important problem because optimal pooling configuration can really change the performance of the basically standard models. The common NAS methods often fail to find the optimal configurations. We also showed that because of the search space search space design that is necessary for a problem, this leads to full weight sharing, which contributes to the suboptimal neural architecture search here. And we proposed a balanced mixture of SuperNets that basically reduces the weight sharing by specializing and associating correct associating models to different pooling configurations. So there are some possible future directions. One of them is trying to reduce the computational cost of the search. So basically, because we always do the random sampling in the configurations, we still keep sampling the architecture or configurations that are not really good. So we have to basically find a better sampling scheme so that we can focus more on the better architectures, but we have to make sure that it does not really like eliminate the architectures that have like potential to perform better later in the search, because that's a possibility. We also should consider the computational cost constraints on the found architectures, because many of the architectures that we found are more expensive than the default architectures. And because we only cared about the accuracy. And also we can apply this to the segmentation, where it is potentially more important to know the basically downsampling and upsampling positions than a classification problem.
Thank you.
So I think for the same thing, have you only tried the uniform sampling for the configuration?
So with our method, we only did the uniform sampling, but when we had just one model, we also did like different sampling algorithms. But yes, for this, only uniform.
So I guess it's related as well to the segmentation that you were planning on doing in the future, but what happens? So I guess with your technique, you're always reliant on having a good validation set, right? You're always doing an evaluation.
Yeah.
Well, but I'm just wondering what would happen if, let's say, you were in a segmentation problem and you had very few image samples for validation. How would that affect your method?
Yeah, that's a really good question, because even for the classification, when we had a smaller data set, because we tried other data sets, then it would not really work as well. So I'm not really sure how we can address this.
Yeah, I think it's an expected problem in the sense that we try to learn more, because we don't learn just the weights, but we learn also the architecture or part of the architecture of the network. So for doing this, we need more data. If we don't have much data, we don't code.
Yeah. It's a bigger optimization problem.
Yeah, exactly. But we find a way to make it work, because common techniques were not working. And and if we had also, now the one big problem is we need to have data, but in many cases, data is not so expensive to get. The other problem is computation. And for that, for the moment, we focus only on performance, but the plan is next step to add also constraints on computation, so to find an optimal trade-off.
I have a question regarding the weight sharing between the different kernels apply at different levels of down something, if I understood correctly. And you show with your result that not sharing or sharing the weight doesn't matter at the end. It doesn't change the performance of the model.
Basically, yes, what we expect is that if we do not share the weights, we expect to have like better performance because we simply have more parameters to train, right? But we can see here that it does not really get any gain.
But maybe it's a bit misleading because not sharing doesn't mean that it's not shared at all. So each configuration has independent weights. It means.
It means that it's not. How can I explain? It's not shared among different levels of feature map sizes. So each level has different weights.
Okay. But then my question is like, if your fully shared is the same as the not shared with different downsampling size, basically, do you think we can use shared layer, shared the kernel, but in between layers even?
I don't quite understand the question. Can you like
you are showing that with independent on the position on the downsampling, the weights are not changing. And do you think that we can share in the layer wise, like yeah?
Okay, so you're saying that like instead of just sharing among different resolutions at a specific layer, we can have it the same across all the layers?
Yeah, because the same kernel will be applied in a different resolution, so it can be applied afterward. I don't know if it makes sense.
No, but I feel like basically the kernel that we would have at the beginning cannot really be shared at the end of the network because
I mean, there was a paper, for instance, that was doing that with ResNet, where instead of building a ResNet where each layer is independent, it was a kind of recurrent ResNet in the sense that it was using the same layer over and over. And surprisingly, it was slightly worse, but still quite good. So it can be an option, but probably you'll lose a little bit in performance, but you gain in a strong compression number of parameters. But here, as we were aiming for top performance, we didn't try. But it's interesting because it's something unexpected, and there was also another paper about ResNet that were showing that each layer is doing almost the same, so you can skip layers and still get similar results. It is something not really fully understood yet.
Yeah. Yeah, because for me, if you skip or add a pooling layer between two kernels, and it doesn't change basically the features that they are extracted, well, you can use those kernel in every day at the end. So it's kind of related to what you said. Thank you. I had another question regarding the architecture. I don't know, there was the name ResNet 20 and everything with the dataset.
yeah.
No, there was 3 tables.
Oh.
Yes, just. Yeah. The thing that I don't understand is, for example, if we take the ResNet 18, like the search space should be constant. If the architecture is constant, no?
Well, the thing is, there is a difference between the ResNet 18 that is used for ImageNet and Sleeper 10,
Okay.
because there is like a max pooling layer
Okay.
here that we do not have here. So that's
Just a quick one. I didn't really understand the gradient-based methods you're comparing to. So does that amount to a bit like in pruning where some pruning methods will evaluate gradients and try and figure out what are the most impactful parts of the model? Is that the same kind of thing? Like how does that work?
so basically it's a bi-level optimization. So we have parameters that are basically the architecture parameters or the convolutional weights. We also have parameters that are so we have convolutional parameters and architecture parameters. So basically the architecture parameters, so if you have, for example, imagine have like 4 resolutions at the layer. So we would have 4 parameters, and then the probability of selecting that, but the probability that weights the feature map sizes at that layer would be the softmax of those parameters. So basically, we calculate every feature map size at every layer, and then we have a weighted sum of them, and we learn how to weight basically the weights of this weighted sum. And it's done by, so basically we have a back propagation that trains the convolutions, and we have another one that trains the architecture weights.
All right.
Maybe a final question. What do you do when you have many configurations? Like here you try with 36 and you go up to 500. But first of all, with 500, how do you deal with that? Would you at test time you evaluate all of them? And second question, can you go to millions of configurations?
For the first question, so because we had, for example, when we have 560 configurations, we're not gonna, at the end of the search, we're not going to go over all of them and evaluate everything. So we use basically we use the accuracy that we had here. So the accuracy that we calculated here, basically it's the weighted average of the accuracies. So we use that to basically rank the architectures, and we select, for example, top n, and we just evaluate those top n on our validation set. And this seems to be working well. So it means that this weighted average accuracy is a good measure for ranking. And if we have like a larger search space, which is often the case in NAS problems, then we would have to have a better sampling algorithm, and we could have, like, for example, we can use like evolutionary algorithm to basically generate different architectures, so that we do not have to like sample everything uniformly, because this is not really possible.
When you say that you can achieve the weighted average accuracy, like what's like across model?
So across the basically evaluation iterations. Yeah.
Because you compute accuracy on a mini batch. but then you would like the accuracy on the entire data set. So okay, if there are no more questions, thank you again.
Thanks for coming.
Presentation, thanks.
Thank you.